Getting a massive aeroderivative turbine from a dead stop to a self-sustaining speed means pushing thousands of pounds of rotating metal past 10,000 RPM. These multi-million-dollar packages are purpose-built for the most demanding environments, delivering up to 60 megawatts of power to isolated offshore platforms and remote industrial sites. The power turbine section has one absolute requirement. It must spin the attached generator at exactly the right speed to match the electrical grid, typically locking in a rigid 60 Hz output. Across a high-voltage transmission system, frequency is the heartbeat of the grid. If that frequency deviates by even a fraction of a hertz, the entire connected network of transformers, motors, and sensitive industrial electronics is put at risk of immediate shutdown. To engineers tasked with keeping that frequency stable, the logical approach seems obvious. You configure the turbine's control system to hold that 60 Hz target perfectly, correcting for any deviation with zero allowable error. This specific governor command is called Isochronous mode. In this state, the turbine rigidly holds exactly 60 Hz, constantly adding or cutting fuel to correct for any frequency dip or surge, regardless of how much physical load is applied to the generator. For a single machine running in isolated island mode, this rigid, zero-error control works perfectly. But the moment that machine connects to a parallel generation network alongside other turbines, that demand for perfection becomes a severe system vulnerability. Introduce a second, identical LM2500 gas turbine, synchronized and connected to that exact same shared bus. Here, two independent turbine governors try to maintain a 60 Hz target during a sudden load spike. Both detect the deviation and simultaneously attempt to correct it. The result is hunting, massive, uncommanded power swings violently oscillating back and forth between the parallel units. Inside the engine enclosures, this inflicts severe mechanical stress on the turbine architecture. The gas generator core is forced to rapidly surge and choke, causing extreme thermal load fluctuations across the hot section. The turbines themselves are not broken. The root cause of this violent oscillation is a flaw in how the control logic has been applied to a shared system. Instructing two advanced machines to independently act as absolute frequency anchors guarantees instability. By demanding tighter individual control from each unit, the operators create total system chaos. Isochronous mode works when only one unit is active, because that single generator serves as the undisputed anchor for the grid. It dictates the frequency, and the grid follows. This illustration shows two people carrying a single stretcher. If both individuals are rigidly insisting on dictating the exact pace, they will fight each other with every single step, unless there is a dedicated, active digital load-sharing network installed between the packages. Two isochronous controllers are completely blind to each other's outputs. They only see the frequency, attempting to force it to their own reference point. To enable passive cooperation between these massive machines, engineers must introduce an intentional, calculated degradation of the speed reference. They have to abandon the goal of perfect zero-error frequency and implement a proportional response parameter. True system stability on a parallel grid requires an engineered give. Rigid perfection must be traded for mechanical flexibility in order to keep the massive machines from tearing the system apart.
This control algorithm is called Droop mode. In Droop, the internal speed reference is allowed to decrease in direct proportion to the active megawatt load applied to the generator. Plotting speed against active load, this perfectly flat line at 100% speed represents isochronous control, maintaining zero steady-state error. Watch the Droop curve. As load climbs to 100%, speed drops steadily to 96%, demonstrating the intentional performance sag. As load increases, the governor allows a typical 3 to 5% speed sag. It stops continuously fighting to maintain exactly 100%. When multiple units are configured with this exact same downward curve, they naturally and passively converge on a stable split of the total active grid load. This shared give completely eliminates the hunting oscillation. The massive turbines perfectly balance the load without ever requiring any real-time data communication between their separate enclosures. By reprogramming the definition of error into a proportional control parameter, engineers trade a microscopic fraction of frequency precision for absolute unbreakable stability across the parallel grid. This principle extends beyond the real active power governed by the turbine. The generator itself governs another critical component of grid load, reactive power, measured in kilovolt amps reactive. The exact same conflict we observed in frequency control has a direct parallel in stator voltage control. This block diagram outlines an automatic voltage regulator, or AVR. Its role is to maintain specific excitation and terminal voltage limits for the generator. If two parallel units try to rigidly hold perfect voltage without compromise, the system breaks down electrically. Highly destructive circulating currents will flow continuously between their stators, generating massive heat and potential insulation failure. The electrical solution to this is voltage droop. The AVR utilizes a 4 to 10% program degradation to passively and safely share lagging reactive current across the parallel units. Intentional degradation is a universal law of parallel generation. It applies equally to mechanical speed via the governor and electrical voltage via the AVR. Here is a real-world diagnostic scenario for field engineers. This diagram shows an actively hunting grid, with power oscillating wildly between units. The operational fix is clear. Either verify the active load-sharing networks or reconfigure the parallel governors to droop mode to stabilize the flow. In a multi-unit power plant, perfect control is the enemy of stability. Two independent anchors equal a fight. Steady-state electrical stability keeps the plant running. But when a high-power turbine trips offline, the focus immediately shifts to the sudden, catastrophic mechanical events taking place inside the engine casing. When a turbine drops offline unexpectedly, the pressure mounts instantly. Plant management demands an immediate restart to restore the lost grid capacity and avoid financial penalties. But forcing a restart on an LM2500 without accounting for the differential cooling rates between the hot inner rotor and the rapidly shrinking outer casing risks grinding the blades directly into the metal. Understanding this strict 4-hour lockout rule and the thermodynamics of hot rotor rub is the only way to prevent the single most expensive mistake a field engineer can make.